more simple. We're going to ditch the hard stuff, I can tell you that much. So let's look at one more thing on here that we didn't really get to yesterday. And that's this. What's this all about? Well, we kind of mentioned most of it. Goodbye, Artie. Oh, good boy. Hey, I'm in charge of the comedy here, so knock it off. What's all this stuff about? Well, S is a measure of distance. In fact, we have several things that we use to talk about a distance. We can use S. Sometimes we use R, as in the position vector or a radius. D for distance, X or Y or height or range, the horizontal distance of projectile motion. So the distance will go by a lot of different names depending on how you prefer to talk about it and which direction it's in. This particular one, S equals R theta, is a particular type of distance. And of course we can take the first derivative of it and get a velocity and another derivative of it and get an acceleration. So this is like position, velocity, and acceleration in a linear sense. And theta, omega, and alpha are position, velocity, and acceleration in a rotational or circular motion kind of way. And it turns out we can relate them to each other. This distance, S, is the distance traveled around a circular path, around a racetrack, if you will. So we mentioned the other day how V sub t was a speedometer reading. Well, S is an odometer reading. So, and it is important to know that whether you're keeping track of your position around the track in terms of theta or S, the arc length that you've traveled, neither one of these is going to reset automatically when you get back to the start line, right? They're just going to keep building. So we can do more than 360 degrees, we can do a 720, we can do a 1080, and all that good stuff. And the same is true of S. It'll keep building. When you've covered 360 degrees, S is the circumference of the circle, right? So we can kind of compare the radius of the circle to how far we've traveled around the circle. And if we've traveled all the way around the circle, then we've covered the circumference. In that case, the ratio of S to theta would be a measure of how far we've gone. I'm sorry, that's not, let me clean that up just a little bit. So S is a measure of how far we've gone, and theta is a measure of how far we've gone. And the question then becomes, what kind of units are we going to see for these things? For S, typically meters. For velocity, meters per second. And for acceleration, meters per second, or meters per second squared. What are units on theta going to be? Well, just as with the distances, we could use meters, centimeters, kilometers. We have a variety of options, but our preference is for meters. What about theta? What are our options and our preferences there? The preferred is radian, and other options include degrees, revolutions, cycles, and sort of anything along those lines, right? How about omega? So omega is a rotational velocity. Instead of meters per second, we're going to have radians per second. And we could do, degrees per hour or anything you can dream up could work in here. A very popular one is revolutions per minute, also known as RPM. So when you see RPM, I want you to think omega. It's a very common measurement of rotational velocity, right? Pretty much every time you're presented with an RPM, you're going to convert it to a radian per second sort of thing. And it's probably not a surprise that over here we're going to have radians per second squared, and any variation on that would be fine as well. In order for these equations to work, for these equations to sort of make sense and to be true, you need to be using radians. In other words, if you take degrees and multiply 180 degrees by the length of the radius of the circle, you kind of get garbage. If you want to get your odometer reading, S, the distance you've traveled, to get that arc length, theta needs to be in radians. So what do radians really mean then? Well, let's look at the units and see if they can tell us. If we solve that for theta, we can say theta is S over R. Of course, we can also say that it's, well, we can put it in other forms too. But S over R, if S is an arc length, that would typically be in meters, and the radius of the circle would typically be in meters. So somehow we take meters, divide them by meters, which should cancel out, and we get radians. What does that tell you about radians? Radians are essentially unitless, which makes them a little tricky. If you're trying to track your units through your problems like you should be doing, radians are kind of going to show up out of nowhere, as they just did. We took meters divided by meters, which left us with nothing, and we called it radians. So what is a radian? Well, a radian is a unitless comparison of arc length to radius. Okay? So radians are a tricky unit in that way, in that they can kind of show up or they can disappear at will. And we'll see a few cases where that happened. But degrees, revolutions, cycles, and everything, they aren't the same ratio, so you can't just multiply by 180 the same way you can multiply by pi. You wouldn't get the same result. It has to be the correct units for these equations to work. Well, this will all make more sense when we put it into application, of course, but we're kind of laying the groundwork for some things that we're going to be doing here today. And you can see that radians are special and radians are necessary. One of the things we're also going to find is that any equation we see an S, a V, or an A in, we're going to be able to write that same equation using theta, omega, or alpha. So it's a good thing they kind of look like a V looks like an omega just a bit, and an A looks like an alpha just a bit. If you're trying to write these conversion equations, the thing to remember is S equals R theta, V equals R omega, and A equals R alpha all have in common that there's an R in front of the Greek letter. So at some point in life, you're going to end up in a situation where you're going, theta, I need to get theta turned into an S. Do I multiply by R? Do I divide by R? And you can remember S equals R theta. And the way you keep from getting any of those letters in the wrong place, you just put the R next to the Greek letter and you're good. Sound is breaking up a bit. Uh-oh. Ooh, for lots of you. Okay. Let me do a little tweak here. Let's see if that helps at all. I'm just checking connections. You know, sometimes it's nothing more than a weather system moving across the country, something like that. And usually that's a short-lived effect. So theta, so S tracks distance traveled around the circle, so does theta. V tracks your speed in sort of a linear sort of way. Omega tracks your speed in a rotational sense. So we've got meters and radians. We've got meters per second and radians per second. And we've got meters per second squared and radians per second squared. So, and again, and I don't know how much was broken up or how much was understood, but when you write these equations, you're going to, at some point in your life, you're going to be saying S equals R theta, but you're going to question it. And you're going to wonder, was it S equals theta over R or SR equals theta? There's going to be a little confusion at some point. So the way you get it straight, the way you remember it's S equals R theta versus any other permutation, you put the R next to the Greek letter. So the R goes next to the theta, or the R goes next to the omega, or the R goes next to the alpha. Any of those will work for you. So all of our sort of straight ahead displacement, S, our straight ahead or tangential velocity, and our tangential acceleration can all be converted to their rotational equivalents, and we can track our position around the circle using either S, V, and A or theta, omega, alpha. What then is this last line, A sub n? Well, A sub n is the normal acceleration component. And you remember from yesterday, it kind of showed up here, which was equivalent to showing up here. But basically what you need to know about centripetal acceleration, or that normal acceleration, it's what gives rise to the tension in a rope when you're swinging a rock around your head, which of course we do every day. It's R omega squared or V squared over R. How can it be both? Well, V equals R omega, as it says here. So I can take these two V's and call it V squared equals R squared omega squared. And I can take V squared over R and turn that into R. Oops, I don't know why I wrote it 2 there. V squared over R then becomes R squared over omega squared over R, or R omega squared. So V squared over R is the same as R omega squared. So if I give you a velocity in meters per second and I ask you for centripetal acceleration, you use V squared over R. If I give you a velocity in radians per second, then you're going to use R omega squared. So just follow the units. Most of the time, I'm going to give you a velocity in revolutions per minute, and that is also an omega. Just need to fix the units a little bit. Now, let's look at this mysterious handbook of ours, which we've already kind of warned you about is going to be a bit of a pain. And we're going to color code these equations. We're going to start with the red equation. Depending on the units of omega and velocity, remember, we're going to be really picky about omega's units. It has to be radians per second. And if it's radians per second, then whatever R is, if R is in meters, then V is going to be in meters. Okay, so the linear things like S, V, A, and R have to agree. In other words, you can't have kilometers in one and expect meters to come out. If one of them's meters, the other's meters. But theta, need to get it down to radians. Wherever you start, convert it to radians. Omega, convert it to radians per second, and so on with radians per second squared. Yes, basically. Now, once we've got an idea of what A is, we might have to figure out what S is over a given length of time. So given a particular acceleration or initial velocity, we have to be able to sort of fluidly move between S, V, A, and of course time factors into that as well. So we're going to start looking at the equations for that. And there are 3 equations we principally use, and you're going to see these equations sprinkled all throughout the dynamics section of the handbook. My favorite, A equals delta V over delta T. Now, one other simplification we haven't mentioned yet that they're going to do for you is, on this exam, the problems are going to involve constant acceleration. Which means, how do we get a constant acceleration? Well, we apply a constant amount of force to a mass, F equals ma. So if we have a constant application of force, then we get a constant acceleration, and that's going to simplify our problems a little bit. So we don't need to worry about this variable A column over on the left so much. We're going to worry about the constant A column on the right. So I've written A equals delta V over delta T. If Let's draw a graph, and this turns out to be a very useful sort of graph, velocity versus time. And let's say we have a varying amount of acceleration, then our velocity could be changing over time. And if we wanted to know the effects of that, if we wanted to measure acceleration, for example, from this graph, we'd have to sort of zoom in on a tiny little area and say, at this instant, the acceleration can be calculated by looking at the change in velocity over the change in time. And when we're looking at a tiny instant like that, we use dv over dt to indicate a tiny differential bit. However, on our exam, what we're going to be dealing with is a constant acceleration. So pretend I just drew a straight line there. In that case, I can look at a tiny little area and look at the change in velocity over the change in time. But that would give me exactly the same result as if I looked at a larger area or even the entire graph. So let's say we go for 20 seconds, so from 0 to 20 seconds, and our initial velocity here is 15 meters per second. What's our acceleration rate going to be? Well, our red equation, A equals delta V over delta T. What's our change in velocity over this process? We're going from 15 to 0, right? So our change is a drop of 15 miles an hour. Now, the question is going to come up, is this a negative acceleration or a positive? And we want to find a consistent way of doing this. So let's just explain a little bit. We're doing V final minus V initial, and we're going to put that over T final minus T initial. What's our initial time? Our initial time for just about every problem you can ever imagine is going to be 0. So it's really common to have a couple of different speeds written over one time. When you do that, you're writing the T final down, and then you're subtracting the T initial, which is 0. Okay? So whenever you only see one time, there's always a kind of an implied minus T naught over here that dropped out. Well, maybe that'll help you remember that on the top, you better write down your final and then subtract the initial. So our final velocity is 0, and we're going to subtract our initial. So it's final minus initial on the top, and final minus initial on the bottom as well. So our acceleration then turns out to be a negative 3/4 of a meter per second. And again, it wouldn't matter how close we zoomed in on this. It's the same acceleration anywhere on the graph. So we'd get the same result from this that we do from that. So A equals delta V over delta T is going to work just fine for our constant acceleration problems we're going to see on the exam. So in our example here, A equals negative 3/4 of a meter per second. And graphically, what is that? That's a slope, isn't it? That's a rise of negative 3. And remember, we always measure slopes from left to right. So I try to clean up my graph. There we go. So A is the slope. We have a rise of negative 3 meters and a run of 4 seconds. So as predicted, the derivative of the velocity versus time graph is its slope. And you're right, it's meters per second squared. We're dropping 3 meters per second every 4 seconds. Sorry about that. Thank you for pointing that out. So that whole meter per second squared, well, it's really how many meters per second do you lose every second? All right. What about this graph? So we've got a graph now that tells us A, and we only need one value for that. And we've got velocities, 15 all the way down to 0. We've got times, 0 through 20. What about this graph tells us the distance? That's sort of the only thing we're missing here. Is there anything about this graph that can indicate the distance traveled for us? Well, let's kind of look at it this way. We're going to call distance S. And if we line up S, V, and A, to get from V to A, we take its derivative with respect to time. What's the opposite of that? If we wanted to get from A back to V, what could we do? We'd have to integrate, right? Well, to get from V up to S, we also have to integrate, or we could go down using a derivative again. So if we take our velocity versus time graph and integrate it, well, what does integrate mean? Integrate means to add up everything, to pile it all together, to integrate it into one big amount. What we're literally doing when we integrate is we're adding up all of the area under the graph. So you tell me, what is the area under my velocity versus time graph? So the S is the area. It's going to be 1/2 base times height. Our base width is 20 seconds. And our height is 15 meters per second. Looks like 150 meters we covered. So we started at 15 meters per second. We dropped to 0 over 20 seconds with a uniform acceleration of -3/4 meters per second squared, covering 150 meters. And so that graph, that velocity versus time graph, is pretty illustrative, isn't it? Pretty neat. Well, so let's look and see where on this page, at least, we see our red equation. I've written it here in my preferred format. It also shows up here. And this is it, too. Look real quick at that and see if you agree that that's V final equals V initial plus AT. That could be written as V final minus V initial over T equals A. All they've done is they've left out the sort of minus T initial on there that we know we usually leave out anyway. So this is the red equation as well. But my preferred form for it, the one that's easiest to say, is A equals delta V over delta T. So we're going to call this next equation the blue equation. And it gives us a method for calculating S. Well, graphically, we already did that, right? We already figured out it's 150. How is this equation going to give us the same result? We can just go ahead and write it here. S equals 150 meters. Well, looking at this equation bit by bit, we see it starts with a record of what your initial position is. And 90% of the time, your initial position is going to be position 0, right? So we'll just write down a 0 as our starting point. What does V naught T tell us? V naught T describes how much distance you would travel if there weren't any acceleration. Can you look at our graph and tell me how much distance we would travel if there weren't acceleration? If the acceleration were 0, we'd have drawn a big rectangle here. And our displacement would be the area under that rectangle, which is just V naught of 15 times T of 20. So that's 300 meters. So what that's telling us is, if you hadn't done any decelerating, you would have gone 300 meters. So that's V naught T. And then the 1/2 AT squared is going to be 1/2 -3/4 times T squared, which would be 20 seconds squared, or 400 seconds squared. So we're going to see our second squared units cancel out. We're going to get meters out of this. And our answer is going to be, follow the math there real carefully, and you'll see it's -150 meters. Yes, if the velocity were constant, the slope of that graph would be 0, the acceleration would be 0. There'd be no change in velocity over time. Absolutely. So what does negative 150 meters tell us? Well, overall, what this equation is saying to us is S equals S naught plus V naught T plus 1/2 AT squared, which means your position is where you started plus how far you would go if there were no acceleration, plus or minus how much extra area you covered because of acceleration, or how much area you didn't cover due to deceleration. So in this case, our S equals 0 plus 300 minus 150 tells us we started at 0. We would have gone 300 meters, but since we slowed down, we lost 150 meters of that, leaving us with a total of 150 meters. So it agrees with the graphical version quite nicely. So S equals S naught plus V naught T plus 1/2 AT squared. Again, we spent a few minutes covering it in detail, but that's a pretty quick equation to use in practice. So our distance covered here turns out to be 150 meters. And that's our blue equation then. What about the other equation? What's unique about this equation compared to the other two? And yes, we're going to call it the green equation. I like a different format for this one as well. Do you agree that what I've written is the same? I kind of left off the S naught because the S naught is usually 0, but leaving off the S naught part, what I've got here is that the difference in the squared velocities is 2AS. And how is that equation fundamentally different from the ones above it? No time, exactly. So if I define a problem statement without referencing, providing, or asking about time, there's a good bet you're using the green equation. Now, it turns out the green equation is just a combination of the other two. We've used two equations to eliminate that unknown variable time. But that's all you got to know about it. The green equation is the difference in the squared velocities is 2AS. So there we have it. We're going to spend the rest of the day looking for red, green, and blue equations throughout the handbook, and we're going to find plenty of copies of them. How about here? Do you see any of them on this page? So this is another section of the handbook, and here's our red equation. Right below it, again, appears our blue equation. But look at the format it's in now. We've got S, get my little arrow, S equals S naught, the S naught's all the way here at the end, V naught T minus T naught, if you don't want to call T naught 0, you could include that, plus 1/2 AT squared. So there's the sort of half, there's the A, and there's the squared. So this version of the blue equation allows you to keep track of T naught, but you never need to do that. T naught's always 0. If you tell me after 20 seconds we're going to start this process, how much time does it take? I can add in the 20 seconds after I've done all the math, right? So let T naught be 0. And then there's an excellent explanation of what all of the variables are, and then down here at the bottom is our 2AS equation, the green equation. So a little bit of redundancy going on there. We saw on page 72, we saw these equations, and here on 73, we see the same equations. Well, this is the left-hand column of 73, and it turns out in the right-hand column of 73, we see this. This looks vaguely similar, but yeah, your eyes aren't playing tricks on you. You do not have a sudden case of dyslexia. This is the rotational version. So we've got A equals delta V over delta T written again. But what we've done is we've divided by radius on both sides. A over R gives us alpha, and V over R gives us omega. So we can write alpha equals delta omega over delta T. Functionally speaking, when you see an A, you can swap in an alpha. When you see a V, you can swap in an omega. So we can write these three equations exactly the same way. Here's S, turned into a theta, equals S naught plus V naught T plus 1/2 AT squared. So the blue equation is still there. It's just been divided through by radius to make it look like a rotational equation. Instead of saying that the difference in the squared V's is 2AS, we can say the difference in the squared omegas is 2 alpha theta. So you can see it really does end up becoming a direct substitution of the Greek letters for the, whatever you call it, the more usual ones. So the equations aren't that hard to get a handle on. In fact, if you can find them in one spot in the book, that's really all you need. We don't really need them now. We've seen them sort of in 3 places already. Let's back up a couple of slides to this one. We've already mentioned most of what is on this slide, but there is an example here that might help you deal with the whole radian idea. Let's say we have a circle with a diameter of 1. If that's true, then that circle has a radius of 1/2. And we could say that's 1/2 meter or whatever it needs to be. If our motion involves a travel of 2 pi radians, that would be going all the way around the circle. What should our arc length, S, be? Well, if theta is 2 pi and R is 1/2, S equals R theta tells us that the arc length we've traveled should be pi. So we could have it in pi meters or half a meter. What that tells you is that 1 meter was the diameter, and the circumference of that circle is pi times the diameter, or pi times 1 meter, or pi meters. So if you go all the way around 2 pi, your arc length is the circumference. And this equation kind of agrees with all that. I know the numbers flew by pretty quickly there, but basically that's kind of how S equals R theta works. It's a comparison of how much of the circumference you've traveled compared to the radius, and that gives you theta. So theta is a ratio of the distance you've traveled compared to the radius. And since both of those are typically in the same units, radians are unitless. All right, and everything else here we've already mentioned. We did mention yesterday that this centripetal acceleration sometimes is seen as a negative r omega squared, sometimes a positive r omega squared. It's also written as v squared over r, and at one point in the book it's written as v squared over rho, where rho is the radius of the circle, and I have no idea why they used rho in one spot when they could have just used r. In fact, let's look at that section. It's on page 72, and it looks big and scary. It's it's almost amusingly, irritatingly, it's almost comical what they've done here. They've told us that position in the x direction would be x, and velocity in the x direction would be x dot, and acceleration would be x double dot. This is the exact same information they already had on page 72 when they wrote x x dot and x double dot. It's just now the x's are in a column, and here the x's are in a row. Totally redundant, totally useless, nothing to see here. So you can ignore this, there's no new information in it. Here are our polar coordinates with all the mess that we found where we ended up with 4 different acceleration terms and it was really messy and all. Well, now they've added a 3rd dimension. So now we're talking about cylindrical coordinates. So we can take our circle described by polar coordinates and give it some height, and it becomes a 3-dimensional tool called cylindrical coordinates. It's not really interesting because the z coordinate is handled just like you do in Cartesian. So there's really nothing to see, nothing to worry about. You can totally ignore this. The next is even worse. It's normal, tangential, and beta coordinates, NTB coordinate system. Totally useless. Nobody cares about this stuff. V is the first derivative of position. A is the first derivative of velocity. We know these things. We don't need them. A equals delta V over delta S. So that's a weird one. It has to do with the whole beta idea. So ignore that one lest you get really torqued up and confused. I think that's actually just a typo and they meant to write T. Don't you think? Here's our normal acceleration, and it's v squared over rho, where rho can be figured by comparing the x and y values, the square of their derivatives over the, oh my goodness, it gets nasty, doesn't it? Well, it's a good thing nobody ever cares about this equation, and I've never seen it used in any problem at all. So this whole section on particle curvilinear motion, laugh at it, cast it aside. If you were able to, when you're working during the exam and you see this section of the handbook come up on your screen, feel free to break out a bottle of whiteout and just paint over it on the monitor. Don't do that. It's not. That was a joke. Don't bring whiteout and mess up their screens. So you can ignore the whole particle curvilinear motion mess. It's got typos in it and it's kind of a mess. Let's see if all of this information I've been throwing at you at lightning speed is useful at all by working a problem. The turntable starts from rest and accelerates. All right, let's just stop right there and ask what this means. What kind of variables and quantities does that give us? T naught equals 0 implies the start, so that's fair enough. From rest means at that initial time, our velocity is 0. Where'd my cursor go? There it is. V naught equals 0. If I remind you that V equals R omega, what else can you tell me? So from rest means V naught equals 0, but it also says one other thing, which is omega naught is also 0. So whichever one of these turns out to be most useful in our problem, we've got them both. All right, it accelerates uniformly at 1.5 rad per second squared. What am I going to label this number? It's an acceleration. Alpha, there you go. So looking at the units, I can tell that this particular acceleration is a rotational acceleration, alpha. Very good. And that's simply based on its units. How many revolutions does it take? Well, if the question is revolutions, what variable can be converted back and forth to revolutions? Yeah, revolutions can be converted to radians, which is our preferred unit of theta, exactly. So the question here is, what is theta? and then we'll do a little conversion to get from radians to revolutions. So how many revolutions does it take for the rotational frequency? Ooh, that's an interesting word. Here's what I don't want you to do. I want you to stop associating the word frequency with the letter F. It's a terrible idea. It's done all over the place, all over the world. Frequency should never be associated with the letter F. Frequency is omega. Why is that important? That's important because not a single equation we've looked at so far involves the letter F, which makes F kind of useless. But lots of equations we've looked at involve omega, so let's just memorize that frequency is an omega. So how many revolutions does it take for the rotational frequency to reach 33.33 RPM? So what variable do we put here next to our 33.33? Omega. Now I could have said how many revolutions does it take for the velocity to reach some number of meters per second, right? And then you do the V equals R omega thing and turn that velocity into an omega, and then off you go. But we don't have to do that. They've already given us the omega. So the rest of this slide asks basically all the questions we've just answered. And a reminder here at the bottom, the preferred unit for omega is radians per second, so we are going to have to convert that. It's not optional with radians. You have to convert it before you can use it. When other units are used, it's often called frequency and denoted by F, but that is a bad habit and it's useless because F doesn't show up in your equations. Omega does. So what do you think then? We've got an omega naught equals 0, we've got an alpha, and we've got a final omega, and we're looking for a theta. Let's see what we could do with this. Well, one of the equations we might apply to this, we're looking for theta, and that's a position. So let's, based on our idea of S equals S naught plus V naught T plus 1/2 AT squared, let's write theta equals theta naught plus omega naught T plus 1/2 alpha T squared. It's a good translation, right? We've memorized one version of the blue equation, and we know we can sort of translate it into rotational terms. Good, so we've got that equation here. Now, we've discovered that our theta naught, we're going to use 0. We're going to start at a position of 0. Fair enough? So that one's going to go away. Starts from rest implied that omega naught was 0, so this one's going to go away. Which means our equation simplifies quite a bit, doesn't it? So after all this mess, all we have to deal with is theta equals 1/2 alpha T squared. Now, you've mentioned in there the conversion. I see in the chat window 360 over pi, very close, but keep in mind a complete revolution is 2 pi radians. So you can write 360 over 2 pi as a conversion factor, or you can write 180 over pi. And we'll do that here shortly. In fact, it's sort of right there. So we've got our blue equation boiled down to this. What's the problem? The problem is it's got a t in it, and we don't know what to do with t. Well, you probably know what we should have done. Well, let's show you what we can do from here. We can use our red equation. A equals delta V over delta T. We can translate it. Alpha equals delta omega over delta T. We can solve this for time and say that time minus T initial, which is 0, equals delta omega over alpha. So now where we've got a T in here that we don't like, we can just drop in an omega over alpha, delta omega over alpha. Since our omega naught is 0, then our delta omega is just omega final. So here's our equation, 1/2 alpha T squared becomes 1/2 alpha omega over alpha squared. A little bit of cancellation gives us omega squared over 2 alpha equals theta. Let me rearrange that a little bit, and if we write omega squared equals 2 alpha theta, does that look a little bit familiar? That's our difference in the squared velocities equals 2as. We'll drop the initial velocity and convert it to rotational. So we just derived the green equation for no good reason, right? So we could have started this problem if we had realized from the beginning that time is not mentioned in this problem and time's not asked for, then we could have just gone straight to the green equation. That would have saved us a little bit of trouble. But since we didn't do that, we have had a good look at all three equations and how they all fit together and how they relate to each other. So very good, then theta equals omega squared over 2 alpha. Let's just plug in our values. When it's time to use omega, we know it's 33.33 revolutions per minute. To get that in our preferred units, we need to convert the revolutions to radians. So we'll put revolutions on the bottom, we'll put radians on the top, and it turns out 1 complete revolution is 2 pi radians. And then to turn minutes into seconds, we'll remember that 1 minute is 60 seconds. So there we go. We've got our multiply by 2 pi, then divide by 60. And after we've done that conversion, we can square it. And then our equation finishes out by dividing by 2 alpha, which is 2 and 1.5 radians per second squared. We get 4 radians. Let me read in the chat window how. Wouldn't the first equation, you mean this one here? Okay. Well, let's see. The idea that I put forth here was S equals S naught plus V naught T plus 1/2 A T squared. What if we divide both sides by R? S over R, given S equals R theta, is a theta. And as we divide each of these terms by R, we get S naught over R, which is theta naught, plus V naught over R, which is omega, times T, and 1/2 AT squared divided by R turns into our 1/2 alpha T squared. So because we're dividing both sides by R, we get our translated equation. Cool? No problem. So, hey, we've done all this work and we found out that theta is 4 radians. And so you go back to the person who asked you this question and you say, 4 radians. And they're like, what? I don't even know what a radian is, man. So we got to turn it into revolutions because that's what they asked for. So we're sort of backtracking our conversion here. We got to undo it. We got to turn radians into revolutions. But we know that 1 revolution equals 2 pi radians. Have we talked about units conversion enough? You want to do a little 2-minute deal on units conversion? All right. A times what still equals A? 1. Exactly. Turns out I can multiply by unity as many times as I want. It can be a times 1 times 1 times 1. I can keep multiplying by 1 all day long, and I won't have screwed anything up, which is an important goal in life. Well, another way to represent 1 is with any fraction, so long as the numerator equals the denominator. Right? So I could use any of these. And I can use them as many times as I feel like it. Or I could use that one. Those are all the same value, aren't they? As long as you're writing a fraction and the numerator equals the denominator, you can multiply it through there and nothing is going to get really screwed up. So that becomes useful when we want to keep track of the numbers as the words or the descriptions of them change. So if I have 5 kilometers and I want to convert it to meters, I get to multiply it by anything as long as the top equals the bottom. And the sort of effective way to do this, if I have kilometers and I want to get rid of them, I put kilometers on the bottom. Anything kilometers can be equated to can go on top. In this case, I want meters. And so now the words will cancel out and the numbers will work together to give me my 5,000 meters. So that's all we're doing with any unit conversion. The numerator has to equal the denominator. So if you say 4 quarts equal 1 gallon, you can make that into a fraction. It can be quarts over gallons or gallons over quarts. It doesn't matter. Whichever one you need is fine. So if we've got radians and we want to turn it into revolutions, let's say we've got 3 radians for some odd reason. Well, I need to make a fraction. I need to put something I want to get rid of on the bottom and what I'm willing to end up with on the top. And it turns out that it's 2 pi radians that equal 1 revolution. So off you go. That's all we're doing anytime we do a unit conversion. And we don't have to do just one at a time. As we saw on the previous slide there, we were able to do a couple of unit conversions. Let me flip back to that. Sort of with on the same line, we've got revolutions per minute. We can get rid of the revolutions. They're going to cancel out and leave us with radians. And we can get rid of the minutes and leave us with seconds. And so we sort of get exactly what we want out of it just by multiplying by these conversion factors we've made up. So any conversion factor is valid so long as the numerator equals the denominator. Good? That's all you got to know about units conversion, really and truly. There's a section on page 72 called relative motion that is just about as useless as most of the other stuff in the dynamics section. Why is it useless? Well, the concept's useful, but the thing is, you already know it. I'm going to give you some sample problems here. I'm taking way too much time to draw a really nice train car. There's a train car. We're going to call it the A train. Here is a bicycle. So your friend is riding a bicycle on a train. I know you're impressed with the artwork. You don't have to thank me. You're standing over here watching this from a fixed reference position on the ground. Yeah, this might be Kevin, but he looks like he's pedaling a little harder than Kevin would. So what can we say about relative position, velocity, and acceleration for this? Well, let's say that our bicyclist, so we'll label it B for bicycle, the velocity of the bicycle with respect to the A train is 5 meters per second. So if there were a speedometer on that bicycle, it would read 5 meters per second. If the train is moving at 3 meters per second relative to you and the rest of the world, what is the actual velocity of the bicycle? I'm going to have to be careful because one of these days I'm going to have somebody named Kevin in the class. But is there one? Oh, there is. Yeah, it was some other Kevin. Surely we didn't mean you. No wonder he's been so quiet. So what's the velocity of the bicycle? So the bicycle relative to the A train is 5 meters per second, but the train relative to you is 3 meters per second. Pretty sure the velocity of the bicycle is actually 8 meters per second, right? You thought we were talking about you? No, that's from an example we used last week. Maybe you missed that class. If you missed that class, then yeah, you thought we were really picking on you. No, that was some other Kevin. So it turns out 8 equals 5 plus 3. So that's kind of saying the velocity of the bicycle is the velocity of the bicycle with respect to the A train plus the velocity of the A train, which is exactly what's written right there. So you didn't really need an equation to solve this, right? You kind of intuitively knew this. In fact, you might not even occur to you to go looking for an equation, and that would be a really good thing. If you can rely on common sense and not go digging through a book for an equation, that's good, because we want you to kind of be an engineer, not a librarian. I don't have anything against librarians. It's just this is the PE exam, not the PL exam or whatever librarians would do. I have no idea. What if we want to talk about accelerations? Well, let's say the bicycle is accelerating at 5 meters per second squared, and the train's accelerating at 3 meters per second squared. What do you think the actual acceleration might be? Probably 8 meters per second squared, right? What if the front of the bicycle is 5 meters from the back of the train, and the back of the train is 3 meters from you? Then probably the front of the bicycle is 8 meters from you. And that's this equation here. So when we do these transformations from one frame of reference to the other, we often do them intuitively, but the equations are listed here if you are disposed to use them. Now, one thing they did that's kind of annoying, notice here they said VB equals VA plus VB over A. And here they said VA equals VB plus VA over B. They flipped all of the subscripts. Why did they do that? Well, they did that because they're completely disorganized. But certainly if we flipped all the subscripts around, that doesn't actually affect the equation. They just swap subscripts. Now, how does the speedometer on a bicycle actually work? Well, it's usually got a little sensor here, and it's tracking how often the wheel rotates. So we're really picking up the wheel speed, which is an omega. But if we know the radius of the wheel and how fast the wheel is rotating, then we can say V equals R omega. So now our speed of the bicycle can be thought of as an R omega of the wheels. And so they've got that here. We can, instead of using a velocity, V, we can use an R omega. Now it is unfortunate they flipped all the subscripts, so our bicycle B and our train A, all that stuff's backwards. But they basically got velocity of the bicycle equals velocity of the train plus R omega of the wheel of the bicycle. So that's what that equation's all about. If we do that one step further with the A's, we can use the A equals R alpha idea here. If we wanted the normal acceleration, that's R omega squared, that shows up there. So we can do that, but that's a little bit crazy. We don't really need to mess with any of that stuff. So this section of the handbook on page 72 be very good. You know, they do major releases like 9.3, 9.4. So we've been on 9.4 for a while, but they keep sneaking in little fixes. So some of the typos that were in there originally and some of the weird subscript stuff that was in there originally, they just kind of sneak in there and they don't tell me about it. So that would be very good if they've used sort of consistent subscripts throughout these sections. So that's relative motion. You can use that as a translation or transformation of axes. Say, well, if I'm 8 feet from here and this is 10 feet from there, I must be 18 feet from there, sort of idea. One of these days they're going to call me. One of these days they're going to call me up and say, why are you trash talking the dynamic section of our handbook? And I'm going, it's finally about time I got your attention. Let's fix this thing. Projectile motion is a big deal in dynamics. Everybody wants to know if you can figure out projectile motion. Well, I bet you can. Here are some ground rules for an object that's undergoing projectile motion. We need to look at an object such as a cannonball or a baseball or a BB or a bullet, anything that's just kind of floating through the air on its own. This doesn't apply to rockets, right? Rockets continuously push themselves. Airplanes continuously force themselves to accelerate and that sort of thing. But an inanimate object tossed into the air is going to undergo projectile motion unless it's like a frisbee or something that actually flies. So what forces are acting on a baseball as it goes through the air? Well, depending on how you spin it, it might do different things, float different ways. That's all due to wind. And our first rule for projectile motion problems is we're going to ignore the wind. All right? So now we have a baseball flying through a vacuum. What forces are acting on it? Well, there's nothing touching it. There's nothing pulling on it except gravity. So the force due to gravity is mg. And that's pointed downward. Well, the force is the weight, which we can call mg. What kind of acceleration does that cause? Now, hopefully you can kind of tell the acceleration is g. It's the acceleration due to gravity. And it's pointed downward, so let's just put a negative sign in front of it. So our vertical acceleration is negative g, negative 9.81 meters per second squared. What's our horizontal equation? Our horizontal acceleration? There is none. Very important point, believe it or not. There is no horizontal acceleration. Let's draw a velocity versus time graph for the horizontal motion. What's it going to look like? Here's time. Here's our velocity axis. If we're just looking at the horizontal velocity, what's our velocity versus time graph going to look like? Well, if the horizontal acceleration is 0, then if we start out moving left to right at 20 meters per second, we're going to keep moving at 20 meters per second for all time until we hit something. So how do you figure out how far you've gone horizontally? Well, you find your horizontal component of velocity and you multiply it by time. Let's say we have a time of 10 seconds before we hit the ground or something. You'd cover 200 meters. So our horizontal distance covered depends only on initial velocity and time. That's pretty convenient. How much time do we have before we stop experiencing projectile motion? Well, however much time there is between launch and landing determines how long a time you can do that horizontal motion, and that's how far you're going to cover. How do we know when we hit the ground? Well, let's draw a velocity versus time graph for the vertical motion. And it's going to look something like this. So here's our velocity in the y direction, and here's time. And it looks like a parabola. At some point, the velocity reaches a maximum. I'm sorry, I didn't actually want to do velocity versus time for this. That's an incorrect graph. I was thinking height versus time would look like a parabola. Sorry about that. A velocity versus time graph, our vertical velocity over time is decreasing. And in fact, it will get negative at some point. What's a negative vertical velocity mean? That just means you're moving downward. So a height versus time graph shows us kind of increasing in height and then dropping down, and that should be a parabola. Kind of try to clean it up a little bit and make it look like one. And what that indicates is we're going up for a while, and then eventually we stop going up and we start going down. Let's say this time is, well, we'll just call it T max. That's the time of our maximum altitude. Where is T max on my velocity versus time graph? It's right there. So what happens is we start out with a positive upward velocity, and we lose velocity because we have an acceleration of negative g. We're losing velocity at a constant rate over time, and at some point we pass a velocity of 0, which means we're no longer moving upward. That's the apex of our travel, the top of our trajectory, and then we start our way back down and hit the ground. If we hit the ground at the same height we were launched from the ground, then the distance traveled up equals the distance traveled down, which means all this area equals all of this area. So there's sort of T final over there. So things look very symmetrical if your launch height and landing height are exactly at the same elevation. Do you remember back in an algebra class, maybe like, I don't know, somewhere between 8th and 10th grade, you started graphing things, and we said to find the minima or maxima of a graph, you find the points at which the derivative of the function equal 0. Well, the derivative of height with respect to time is velocity. So that's exactly what we're doing here. The derivative of height with respect to time, the angle of this graph, is the velocity, and we're looking for a point at which the velocity equals 0 as we've reached this flat spot on the top of the curve. So that all works. So how do we do this? Well, if our goal in a projectile motion problem typically is to figure out how far we've traveled horizontally. So to figure out that horizontal travel, we need the initial velocity and time. To figure out time, we need to sort of solve that height problem for the time involved before impact. The area under the line is the distance traveled. So the integral of that velocity versus time graph is distance. Now, when we do projectile motion, it's common for some people at least to use the term h for height and r for range. You could just as easily use y values for height and x values for range. I'm going to use h and r for the simple reason that I want you to associate the term range with horizontal movement. So a typical projectile motion problem, they're going to ask you for the range. And what they mean by that is the total horizontal distance traveled. Let's take a look at a projectile motion problem. And what you're going to see is that we write an equation for h, we solve that equation for time, and we use the time to get the range. That's a typical projectile motion problem. Let's see if we can do that here. A projectile is launched at 180 meters per second at a 30-degree incline. The launch point is 150 meters above impact. So now we look at our figure, and sure enough, we see a 150-meter difference in elevation and our 30-degree launch angle. They're going to ask us for the maximum height, the flight time, and the range. So how do we do all that? Well, we can go back to our red, green, and blue equations and write an equation for height. Well, height is another version of position, right? So just as we wrote S equals S naught plus V naught T plus 1/2 AT squared, we can instead call it height. H equals H naught plus V naught. We're going to make sure we only use the velocity in the vertical direction or Y direction. And we're only going to use the acceleration in the Y direction as well. Okay? Well, if we're going to find the maximum height, then we need to find this point here where the velocity equals 0. How do we get velocity from a height equation? We'll take the derivative of that equation with respect to time, or we call it h prime. And if we'll set that velocity equal to 0 and solve for the time, that will tell us how long it takes to reach the top, and then we can plug that time in here to get the height at the top. So let's figure out when we hit that velocity. What's the derivative of h naught? Well, h naught is a constant value. In fact, in this case, it's just 150 meters. H naught is always 150 meters throughout the duration of this problem, so it's not changing over time. So the derivative of h naught is absolutely nothing. The derivative of v naught y t is v naught y, and the derivative of 1/2 at squared is 1/2 times 2 at. So our final velocity, or at the top of this thing, final just for this little portion, equals v naught plus at. Does that equation look familiar? Oop. Well, I'm taking the derivative with respect to time. So the derivative with respect to time of t squared equals 2t. So that's where I got the 2, and that's why it's not squared anymore. Right? So my 1/2 at squared has a derivative of at. Does that equation look familiar that I just wrote? The Vf equals v naught plus at? How about if I rearrange it just slightly and write it as a equals delta v over delta t? The derivative of the blue equation is the red equation. Not that you have to know that, but it's true. So we could have just started with our red equation here and said our final velocity is our initial velocity plus at. We're looking for a point at which the velocity is 0, so we'll say 0 equals v naught plus at, and we're trying to solve for time. So let's just rearrange this and solve for time. We'll say t equals vf minus v naught over a. I know I'm doing the algebra kind of quickly, but hopefully you follow it. So we're looking for the time reach the top. Our V final is, we're going to set that equal to 0. What's our V naught value going to be? As a reminder, everything we're doing right now is purely in the vertical direction. So what we're really looking for here is V naught Y and A in the Y direction. Yeah, absolutely. So if we've got 180 meters per second at a 30-degree angle, what's this vertical value going to be? It's going to be 90 meters per second, right? We're at a 30-degree angle. So it's going to be 180 sine theta. Or 180 sine 30, yes. So we've got 0 minus 90 meters per second, that's 180 sine theta, over AY. What's AY? Minus 9.81 meters per second squared, which is about 10 seconds. It's actually 9.12 seconds if memory serves. So it takes us just over 9 seconds to reach the top. Let's go back and see if that makes sense a little bit. Let me ask you, just looking at this graph here, what we've got is a graph of height versus time, but we can kind of sketch on here what our velocities are. What's our vertical velocity at this point right here when we're launched? That's our 90 meters per second value, right? Does everybody agree on that 90 meters per second vertical launch velocity? So that's 90. 1 second later, what's our vertical velocity? If I throw something up in the air, it's going to slow down, right? So it's going to be less, a second later, it's going to be less than 90. In fact, it's going to be 80 and change. We're going to be losing 9.81 meters per second every second. So 9.81, what is that? 80.19? 80.19, I'll just scratch that one in there. So about 80. And then a second later, it's only going to be going up at 70 and change, and then 60, 50, 40, 30. By the time it reaches the top here, its vertical velocity will be 0. And that takes just about 10 seconds, a little less than 10 seconds. After it's reached the apex, which happens at 9.12 seconds, I hope I got that number right, what's its velocity at 10.12 seconds? We need a slight correction on that. Oh, okay, well that's more accurate, but still wrong. 9.17. Okay, so maybe it's 9.17. Yeah, it's due to gravity, right? It's going to be negative 9.81 meters per second. So we reach the top, and then we continue the same process. We're still losing 9.81 meters per second every second. So that's at about, 10 seconds and change, and at 11 seconds and change, we're going to be at 19 point something negative because it's downward. And then we're going to keep increasing in velocity downward until we hit something. So we really are losing 9.81 meters per second every second. All right, so that's obviously way more explanation than this problem really needs. But the important thing is when we're asked for the maximum height, we're going to solve for that time, and everything on this slide is what we've talked about, 9.18 seconds. So I kept saying 1, 2. It's 9.18 seconds to reach the top. Good. It's not exactly what we asked, though. We asked for the height. So our maximum height basically just requires us to punch that time in to our height equation. So S equals S naught plus V naught T plus 1 half AT squared. We're using just the vertical version of that, or we call it height. Our maximum height depends on H naught, our starting point at 150 meters. Our V naught T, which is 180 sine 30, which we agreed was 90 meters per second. V naught T, where we add the T in that we just found, and our T is 9.18, so there's that. And then we'll use another 9.18 or 2 as we square it here in the 1 half AT squared part of the equation. Little algebra runs through there. You can see we started at 150 meters. We would have gone 826 more meters, but we decelerated. So in 9.18 seconds, we traveled 563 meters, or we traveled to an altitude of 563 meters. Okay, so that is basically the most difficult projectile motion problem we see on the exam. Find the maximum height. It's the most difficult one because people get hung up on how to find that maximum point, but all you got to remember is that's the point at which you run out of velocity. So we'll start with a velocity equation, set velocity equal to 0 and solve for time, and then ram that time back through our position equation to get the final height. Now our next question was the total flight time to impact. So how long does it take to get all the way over to there? Well, you know, it's kind of interesting. This graph here, this parabolic graph, is actually a graph of height versus range, but it looks an awful lot like a graph of height versus time, doesn't it? Why is that? Well, we did kind of mention that our horizontal velocity is, I'm sorry, got that backwards. Our horizontal distance traveled, range, is going to be our initial horizontal velocity times time. That's V naught in the x direction times time. Well, that's a constant. It's not going to change. So R and T are proportional to each other. So you can think of this as a graph of height over time or a graph of height over range. It's going to look identical. So let's look at this question of total flight time. To get total flight time, what we need to do, again, the flight time is not governed by anything horizontal, is it? You stop flying when you hit the ground, essentially because you run out of height. So let's go back to our height equation. And instead of finding just the height to the apex, we're going to find the height all the way to the impact point. What is our height at impact? Can you tell based on this? What are we going to use for height at impact? Yeah, it's down here at 0. And our H naught we've been using is 150 meters. So if we set up an H final equals H naught plus V naught in the y direction t plus 1 half a in the y direction t squared, our values are 0. Final height of 0 equals 150 meters plus 180 sine 30, 90 meters per second times t plus 1 half negative 9.81 meters per second squared times t squared. What kind of an equation is that? Well, first of all, how many variables are left in that equation? There's only one, right? T. So we can solve this thing. So what kind of an equation is that? It's a quadratic equation. So just as if you had like an ax squared plus bx plus c equals 0 kind of setup, well, that looks an awful lot like it. Here's our squared term, there's our single term, there's our constant, and there's the 0. So that's c, that's b, that's a, and there's our t squared and t, and there's 0. So, yeah, you're going to need the quadratic formula. Fortunately, it's given to you in the supplied reference handbook. Applying the quadratic formula to this problem, so the 1/2 a turns into a negative 4.9. So that's our a value for the quadratic formula, there's our b value, and there's our c value. The time at impact turns out to be 19.9 seconds. So it's kind of interesting that we launch up here. It takes us 9.18 seconds to get to the top. And it takes us a total of 19.9 seconds to get down here. When do we pass this point? In other words, when do we come back down through 150 meters? $19.4 seconds, right. So it takes us 9.18 to get up. It takes us another 9.18 to get down. So 19.4-ish. Yeah, 0.36, I guess, right? Is that right? Yeah. At 19.3 seconds, we're back down at 150 meters. And it only takes another half a second because we're screaming down so fast to cover that last 150 meters. Now, we haven't really drawn this to scale, right? Because this apex is up at 563 meters. So it's not really to scale. This would be a, kind of a, more like that would be to scale. Okay, so it takes 20 seconds for us to hit the ground. Now, the most common question in projectile motion is to tell me what the range is. How are we going to do that? Well, our good old blue equation, S equals S naught plus V naught T plus 1/2 AT squared, I bet you don't forget that one, can be used to find range. After all, it's just a horizontal distance, so you can call it X if you want and go like that, but we'll call it range. It's our initial range reading, which is pretty much always going to be 0, plus the horizontal velocity times time, plus the horizontal acceleration times time squared divided by 2. What are those values? Well, R naught's going to be 0. Because we're going to start counting from 0. What's our horizontal acceleration value? Our horizontal acceleration value is 0. So that term's going to drop out, which means, as promised, our range is simply V naught x t. It's proportional to the time it takes. So our V naught x is 180 cosine 30, which is 87% of 180, which is about 157 or something like that. So V naught x times time means we'll take that 180 cosine 30 and multiply it by 20 seconds, and we get about 3,100 meters. Is it a coincidence that the maximum x value of which equation is the time that it takes to get to the highest point? No, that's not really a coincidence, no. So one of the interesting things we find in dynamics is that we end up doing sort of the same things over and over again. So you're going to see a quadratic equation where the a value is negative 4.9 quite often, because it's just half of the acceleration. So you'll be writing the quadratic formula and you'll be going, oh, there's that negative 4.9 on the bottom again, right? Okay, so that's projectile motion. We started with sort of the most difficult version, which is find the maximum height. And then we tackled the question of the total flight time. And the total flight time is pretty much always necessary to find the range, right? So even if I hadn't asked you this explicitly, you'd have to calculate this in order to get that. So to answer this most common question of range, you have to set up your height equation, solve that quadratic equation to get time, and then use the time to establish your range. This is a little bit of a twist on the typical projectile motion problem. Let's look at this one. We're going to talk about it briefly, then we'll give you a break, and we'll give you some time to work it, and we'll turn you loose on it. A bomber flies horizontally at 275 kilometers per hour at an altitude of 3,000 meters. At what angle phi from the bomber to the target should the bomb be dropped? Fortunately, they've given us a diagram to help us understand what they're talking about. Phi is how far an angle ahead you have to look to see your target at the moment you drop the bomb that's going to hit it. Our initial height is 3,000 meters. We could call this a range. And so what we're going to do is we're going to set up the height equation, solve that for time, and use that to find range. Once we've found range, we can use some trig to find that angle. Our final height, hf or h impact, is going to be 0. And what is v naught in the y direction? Well, look at the problem statement here and see if you can figure it out. A bomber flies horizontally at 275 kph. Our v naught in the horizontal direction is 275 kilometers per hour, but our v naught in the vertical direction is 0. We're dropping the bomb. We're just simply letting go of it. It has no vertical velocity at that instant. Of course, it's going to pick up some vertical velocity pretty quickly as it falls toward the ground. So now that we've described that problem, I figure it'll take you 3 minutes or so to at least get a good effort in on it, if not solve it. And we'll give you a bit of a break too. So let's get back here at 7:48.